Today we are going to learn about optimized performance with NumPy array broadcasting. We will explore how broadcasting in NumPy can streamline complex calculations and improve computational efficiency. Welcome to our session on optimizing performance with NumPy array broadcasting. Broadcasting is a powerful mechanism within NumPy that allows operations on arrays of different shapes. This capability is essential for high-performance data processing, enabling you to perform operations without manually reshaping your data. We'll delve into the rules governing broadcasting and see how it simplifies complex calculations, ultimately enhancing your computational efficiency. Broadcasting is not just a time saver, it actually transforms the way data manipulation is approached in Python. Throughout this video, we'll cover various scenarios where broadcasting can be applied, compare it with traditional iteration methods, and discuss common pitfalls and how to avoid them. Understanding the rules of broadcasting is crucial for leveraging its full potential. The core principle is shape compatibility. When you perform operations on arrays, NumPy automatically aligns them based on their dimensions. If the shapes are compatible, NumPy expands the smaller array across the larger one. This means you can perform element-wise operations without explicitly looping through the arrays. For instance, you can add a scalar to an array, and NumPy will broadcast the scalar across each element of the array. This automatic alignment simplifies code and reduces the need for manual reshaping. However, it's essential to ensure that the shapes align correctly. If they're incompatible, NumPy will raise an error. In this block, we'll look at practical examples demonstrating these rules in action, and how they can be applied to streamline data science tasks. Broadcasting is a game changer in data analysis, allowing you to handle various scenarios effortlessly. One typical use case is element-wise arithmetic operations, such as adding a vector to each row of a matrix. This operation doesn't require explicit loops, thanks to broadcasting. Another scenario is data normalization, where you adjust datasets to a common scale without distorting differences in the ranges of values. Broadcasting simplifies this by allowing you to subtract the mean and divide by the standard deviation directly, even if these are stored in arrays of different shapes. Additionally, broadcasting can efficiently scale features across datasets, which is particularly useful in preparing data for machine learning algorithms. In statistical computations, you can apply operations like mean or sum across specific axes with ease. This block will provide a detailed walkthrough of these scenarios, showcasing their implementation and benefits in real-world data analysis. One of the most significant advantages of broadcasting is its efficiency compared to manual iteration. Loop-based methods require explicit iteration over each element, which can be computationally expensive, particularly for large datasets. Broadcasting eliminates the need for loops, allowing operations to be vectorized. This reduction in code complexity not only makes your code more readable but also significantly enhances performance. In many cases, broadcasting can execute operations several times faster than traditional loops. We'll compare these two approaches, highlighting real-world performance improvements. For instance, when processing large matrices, broadcasting can reduce computational time from minutes to seconds. This block will explore these benefits in depth, providing examples and benchmarks to illustrate the improvements in both speed and code simplicity. Despite its advantages, broadcasting can sometimes lead to errors, particularly if the shapes of the arrays are incompatible. One common error is value error. Operands could not be broadcast together with shapes, indicating that the arrays cannot be aligned for the operation. To handle these errors, it's crucial to understand the underlying cause, usually a mismatch in dimensions. To troubleshoot these issues, always verify the shapes of your arrays before performing operations. Use functions like np.shape to inspect and ensure compatibility. Adopting best practices in debugging, such as checking intermediary results and using assertions, can also help prevent pitfalls. This block will delve into these strategies, offering practical advice on how to avoid common errors and maintain robust, error-free code. To fully grasp broadcasting, let's explore some practical examples using arithmetic operations. Consider adding a vector to each row of a 2D array. Without broadcasting, you'd need nested loops, but broadcasting allows you to write a single line of code. Similarly, for multiplication and division, broadcasting lets you apply these operations across entire arrays effortlessly. This capability simplifies complex calculations, making your code cleaner and more efficient. We'll also apply arithmetic operations to multidimensional arrays, demonstrating how broadcasting handles these seamlessly. Real-world scenarios, such as financial calculations, scientific computations, and big data analysis, will illustrate broadcasting's practical applications. This block aims to provide a hands-on understanding of how arithmetic operations leverage broadcasting for computational efficiency. Broadcasting's power extends beyond 2D arrays to multidimensional arrays, which are common in fields like image processing and scientific computing. Understanding how to apply broadcasting in 3D and higher dimensions is crucial for these applications. NumPy aligns arrays across multiple axes, allowing for operations like filtering and transformation to be executed efficiently. For example, in image processing, you might need to apply a filter across a 3D array representing an image's RGB channels. Broadcasting lets you do this seamlessly, without explicit loops or reshaping. However, challenges can arise, particularly with high-dimensional data. Ensuring correct alignment and avoiding memory inefficiencies are key considerations. This block will explore these applications, providing detailed examples and solutions to common challenges in multidimensional broadcasting. Matrix operations are fundamental in many computational fields, and broadcasting can significantly enhance their efficiency. Whether you're performing matrix addition, subtraction, or element-wise multiplication, broadcasting simplifies these tasks. For instance, adding a scalar value to a matrix or performing transformations like scaling is straightforward with broadcasting. In linear algebra, where operations like matrix multiplication are common, broadcasting can optimize these computations, especially when dealing with large datasets. The performance gains are substantial, reducing computational time and improving code clarity. This block will delve into matrix operations, demonstrating how broadcasting can be leveraged for efficient and elegant solutions.
The performance benefits of broadcasting over loops are significant, particularly as datasets grow in size. Broadcasting's ability to vectorize operations means less resource consumption and faster execution times. For instance, operations that might take several minutes to execute using loops can often be completed in seconds with broadcasting. This scalability makes broadcasting a best practice in high-performance computing. We'll examine real-world benchmarks that illustrate these speed benefits, highlighting scenarios where broadcasting drastically outperforms traditional loops. By the end of this block, you'll have a clear understanding of why broadcasting is not only a more efficient approach but also a more scalable one for handling large datasets. As we conclude, it's clear that NumPy array broadcasting is a powerful tool for optimizing performance in computational tasks. Its ability to handle operations on arrays of different shapes simplifies code and enhances efficiency across various fields, from data analysis to scientific computing. The key takeaways from today's session include understanding broadcasting rules, applying them to practical scenarios, and recognizing the performance gains over traditional methods. We encourage you to apply these learnings in your projects, exploring further the advanced possibilities broadcasting offers. Thank you for joining us, and we look forward to seeing how you leverage broadcasting to optimize your computational tasks.